Sometimes compounds can achieve the octet rule by forming multiple bonds. For example, carbon dioxide. Carbon has 4 electrons in its outer shell. Oxygen has 6 electrons in its outer shell. Oxygen, of course, is in group 6 and thus has 6 electrons in its outer shell. So we draw 2, that's 2 for oxygen. Here's another 2, that's 4 for oxygen. And here's another 2, that's 6 for oxygen. So we do the same thing on the other side. Total of 6 for oxygen. So oxygen can bond with carbon with its 4 electrons in this manner. Thus, the octet rule has been achieved. Because oxygen is surrounded by 2, 4, 6, 8 electrons. This oxygen also 2, 4, 6, 8 electrons. So this is a more stable position for it. And carbon has 2, 4, 2, 4. So a total of 8 electrons surrounding the carbon. So each of the atoms is able to achieve the octet rule by doing this special type of bond. And this bond, the way we would generally write it, is simply carbon double bonded to oxygen, double bonded to another oxygen. And this is a multiple bond. Instead of the single bond that we've previously seen, this is a multiple bond. And of course, because of the difference of electronegativity, carbon being to the left and oxygen being to the right, carbon would be delta positive, each oxygen would be delta negative. Another example of the octet rule being achieved with multiple bonds is nitrogen, or N2. And nitrogen would be in the 5th group in the periodic table. Nitrogen has 5 outer shell electrons. And so if we draw nitrogen here in N2, each nitrogen has 5 outer shell electrons. So we'll draw 1, 2, 3 for this nitrogen, and there's the other 2, so this has 5 electrons. Here we draw 1, 2, then we draw 1, 2, 3. So we have 5 electrons here. Now by bonding in this manner, each nitrogen is surrounded by 8 electrons. So this nitrogen has 2, and then there are 6 here, so it's a total of 8 electrons. And this nitrogen has the 6 here and the 2 here, total of 8 electrons. Therefore, each nitrogen, by bonding in this way, by using a multiple bond, is able to achieve the octet rule. So now we have a 1, 2, 3, a triple bond. As you notice, each line represents a pair of electrons, an electron pair. So there's 1, 2, 3 electron pairs. In other words, 6 electrons in the bond between the 2 nitrogens. So these are multiple bonds. There are 2 things to say about multiple bonds. To begin with, multiple bonds are unsaturated. Anytime you see a multiple bond, it means that the atom is unsaturated, meaning that the atom is not bonded to the maximum number of other atoms that it could be bonded to. For example, carbon can be bonded to 4 different atoms, like for example in CH4, methane, which we saw earlier. It could be bonded to 4 different hydrogens. But here, carbon is only bonded to 2 oxygens. It's not bonded to 4 different substances. Therefore, this carbon is said to be unsaturated. It's an unsaturated compound. And this is the case, of course, with nitrogen as well, because it's not bonded to the maximum number of atoms that it could be bonded to in theory. So multiple bonds are unsaturated. The second thing is, multiple bonds are stronger. That is to say that by having a double bond that is stronger than only having a single bond. I am not saying, however, that the second bond in the double bond is stronger than the first bond that was laid down. that is not the case. The second bond is actually weaker. However, by having two bonds, it is stronger than just having one bond or a single bond. And by having three bonds, that is even stronger still than having two bonds or just having one bond. Resonance is a very important concept to understand, since it is one of the foundations of organic chemistry. We will look at the resonance of sulfur dioxide. First, in terms of what the molecule would look like, using the octet rule, remembering that sulfur is in the 6th group and oxygen is in the 6th group, so both have 6 electrons in their outer shell. So here's sulfur with its 6 electrons in its outer shell. So we'll put 2 here, we'll put oxygen here, another oxygen here, and we'll put their lone pair electrons as well. So here we have this oxygen achieving its octet, 2, 4, 6, 8. This oxygen, 2, 4, 6, 2, 4, 6, 8. The sulfur, having its 6 electrons, 2, 4, then it has 6, so it has 2, 4, 6, 8 electrons in its, for it to achieve its octet. So each will contribute 6 electrons. Now, what we have here is a multiple bond. We have a double bond on the left and we have a single bond on the right-hand side. But here becomes the problem. Here's sulfur. This is the other way of writing it. This is the exact thing, just simplified. But the problem is, why isn't it like this? What's the difference? Well, there is no difference. There is no reason why the double bond should be on the left side any more than why it should be on the right side. Because there is symmetry in terms of the electronegativity of these two substances, there's no reason why one would have a double bond more than the other. And so, if you were to do an experiment to determine what side the double bond was on for sulfur dioxide, you would find that there is no double bond in sulfur dioxide. And you would find that we simplify things by writing the bonds as we do. But in reality, because of this symmetry, there is no double bond here at all. What there is, in actuality, you would find with your experiment that sulfur is bonded to oxygen, but that there are electrons which are delocalized, meaning they're not, the double bond is not there, it's not on the other side, but rather it is spread over the molecule. And so you wouldn't find that there is a single bond in sulfur dioxide, nor would you find that there's a double bond. You would find that there's about a bond and a half on each side. And so this idea that there's electrons which are delocalized over a period, they're not localized just in somewhere, they're delocalized over the molecule, that's called resonance. And electrons are able to increase their stability when they are able to have a resonance structure. Now notice, the word is a bit of a misnomer, because some students hear the word resonance and they think that there is resonating, meaning it's going from this to this and back and forth from this. It's not. The actual molecule is this, but we symbolize it either this way or this way or this way. These are just symbols, but the true molecule looks something like this, where the electrons are delocalized over an area. We are now going to look at the concept of molecular polarity in the context of BCl3. This is boron, and this is chlorine. So boron, if you look at the periodic table, is going to be to the left of chlorine, and chlorine being in the 7th group with the rest of the halogens. So we have boron, B, and we have chlorine, Cl, Cl, Cl. Now, because boron is to the left in the periodic table, boron would be delta positive, and the chlorines are all going to be delta negative, as each of the chlorines have a greater tendency, more electronegativity, greater tendency to attract electrons to them. So they are attracting the electrons in the bond. So these are polar bonds. There is no doubt of that. So the question is this a polar molecule? The answer is no. Yes, these are polar bonds, no doubt about that. Each of these connections have a difference in electronegativity. However, if you look at the overall molecule, because of the symmetry, the center of positive charge, well, that would be here. There's only one place where there's something which is partially positively charged. The center of negative charge for the molecule would be also right here. Because of this symmetry, this is a triangle in which at each corner there's a delta negative charge, so the center of negative charge would also be here. Whenever you have the centers of positive and negative charge at the same position, therefore the molecule is not polar, and therefore the molecule has a zero dipole moment. A dipole moment is something that you do not need to know the details of. You don't need to know how it is derived in terms of using polarized light and watching how molecules move or do not move when there's polarized light. But what you do need to know is the definition, and that is there is a dipole moment present when there is a separation of the centers of positive and negative charges in a molecule. When the centers of positive and negative charges in the molecule are in the same position, then there is a zero dipole moment. Let's look at a couple of other examples. For example, water. For water, we have oxygen, hydrogen, hydrogen. So the question could easily be, is there a non-zero dipole moment or is there a zero dipole moment? Well, the center of negative charge will simply be here. That's where it's delta negative. This is delta positive, this is delta positive. The center of positive charge would be this point between the hydrogens. And therefore, there would be a difference between the center of negative and positive charges. Therefore, water would have a dipole moment. We will now look at hybridization. Hybridization refers to the changes that occur within an atom when the atom is about to bond with another atom. For example, let us first look at the electronic configuration of a carbon atom. Now, in order to write the electronic configuration of a carbon atom, you can look at the periodic table, locate carbon, atomic number 6, and because it's atomic number 6, which means it has 6 protons, it must also have 6 electrons. So then we can start filling up our orbitals according to the idea that we have to use up 6 electrons. So we're going to look at the carbon atom. So in the carbon atom, we're going to look at the atom as follows. This box will place the first electrons, which will be 1s. In the next box, we'll place the 2s electrons, and in this box, the 2p electrons. Remember, we have 6 electrons to place. The idea that we're going to draw these diagrams using boxes, it has a very complicated name. They're called box diagrams. And anyway, it helps us to have sort of a bookkeeping for the electrons to watch where they go and where they will end up. So in the first box, in the 1s box, we know that there's a maximum of 2 electrons that can fit in this box from what we've already discussed about electronic configuration. So we're going to put 2 electrons in this box. We remember also that the magnetic spin quantum number can be plus a half or minus a half depending on which way the spin, clockwise or counterclockwise. So we will symbolize the 2 different spins by placing 1 arrow upwards, so it's just really a half of an arrow that we're drawing, and 1 arrow downwards. So this is the symbol for 2 electrons in the 1s box. In other words, this is 1s2. So we go to the second shell. We have 4 more electrons. So we place 2 electrons in the 2s shell. So here's 1 electron, and here's another electron. So we have 1s2, 2s2. 4 electrons have been placed. There's 2 electrons left. So we place 2 electrons in the p. So we'll have 1s2, 2s2, 2p2. So we place our first electron in the p. And the second electron is such that because it's all in the same orbital and electrons are negatively charged, the electrons would rather be as far apart as possible, as energetically possible. And so the next electron, instead of being in the same box, will move on to the other box, 1 level higher, because it would rather not be as too close to the other electrons. So here we have 1s2, 2s2, 2p2. That's the carbon atom. Well, something will change in the carbon molecule. So here's the 1s box, 2s box, and here's the 2p box. Well, this is what happens. In the carbon molecule, the 1s box, it's the same. But the change occurs over here. And this is the reason. If you can imagine carbon having its nucleus and its electrons around it, it would have the first shell, then a second shell. And in the second shell, it would have 4 electrons. 1, 2, 3, 4 in shell number 2. So it has these 4 electrons in its outer shell. Now let's say that it wanted to bond, like for example with hydrogen. So we have carbon atom, we have hydrogen atom, and they're going to bond. Well, this would require significant energy to bring these 2 atoms together, because on the outer surface of the atom there are electrons. They are negatively charged, and the outer surface of the hydrogen there are negatively charged electrons. So as the 2 atoms are approaching, there is an attraction between the electrons of one and the nucleus of the other, but there's also this repulsion between the electrons as these atoms are being brought together. Because there is the repulsion between the electrons, when the atoms are approaching, there is an elevation of the energy. And because there's an elevation of the energy, one of the electrons in the carbon molecule pops up to a higher level. So we have 1 electron here, 1 here, 1 here, and 1 here. So we end up with 1 electron in the s orbital, 1 s electron, then we have 3 p electrons. We have 3 p electrons. Now it's going to make something brand new, a hybrid. It's no longer going to be spherical. It's no longer going to be exactly dumbbell shaped. It's going to be a new arrangement of the electrons in order to be able to bond with this other atom. And that new arrangement is not S, it's not P. It is 1 plus 3, 4, SP, 3, hybrids. So this is a brand new arrangement of the electrons forming an sp3 hybrid. And there are 4 sp3 hybrids because there are 4 electrons. So 4 possible bonds with this new sp3 hybrid. So for example, you have carbon forming one of its sp3 hybrids. Here's another. Here's another. Here's another which is going away from you into the board. These ones are coming out. This is in the plane. And then here I'll draw some spheres at the end of these bonds. And those spheres represent hydrogen atoms. So this would be a representation of CH4. Now you will notice that this forms sort of a pyramid-like structure. And this structure is called a tetrahedron. And the angle between these bonds is called the tetrahedral angle, which was 109.5 degrees. It's 109.5 degrees, which is the normal tetrahedral angle. Now let's say we have another molecule like ammonia, NH3. Well, NH3 has its sp3 bonds, and it's bonding its sp3 hybrid bonds with a hydrogen. So this is NH3. Very similar to CH4, except NH3 has a lone pair of electrons. So these lone pair of electrons, which I'll symbolize like this, are on the nitrogen, and then nitrogen has these 3 bonds. So a common question is, what would be your comment on the difference of the angle between these bonds and between the lone pair and these bonds in the nitrogen? Well, this angle here would be greater than 109.5 degrees. The reason is, when carbon has a bond to another atom, its electrons are moving away from carbon in order to bond with the hydrogen. But when you have a lone pair of electrons, the electrons are remaining closer to the nitrogen atom. Because the electrons are closer in the molecule, therefore these electrons, being negatively charged, will repel the bond with the other hydrogens. And because it repels, it pushes these away because they're like charges. So it pushes this away and makes the bonds down here smaller, but the bonds up here larger. Now we can summarize the hybrid orbitals. So if you were to have a 1s electron plus a 1p, you would create 2 sp hybrids. And as soon as you know that there is an sp hybrid, then you know that the shape of the molecule must be linear. And an example of that would be BeCl2. Now, if you were to have 1s electron and 2p, then you would have 3 sp2 hybrids. So there will be 3 different hybrids, and the shape would be trigonal. And we saw an example of that, which was BeCl3, where boron was at the center of a triangle with chlorine in the corners of the triangle. That would be, there are 3 hybrids there, 3 separate bonds created, and so those are sp2 hybrids. And when you have 1s plus 3p, you get 4 sp3 hybrids. And this shape, of course, is the tetrahedron. So this would be a tetrahedron, And we saw the example of that, which is CH4. So let us look at the tetrahedron with a couple of different molecules and a couple of different hybrid orbitals. Here is a compound that has many different hybrid orbitals. The compound has 2 carbons and it's a hydrocarbon. So it has 2 carbons, so it's eth, and it's a hydrocarbon, so it's an alkane. Therefore it's called ethane. So this compound, each carbon has 4 different bonds. So right away you know that it has to be at the center of a tetrahedron. Each carbon is at the center of a tetrahedron. And so we also know that the carbon would have sp3 bonds. So this bond right here would be an sp3 to sp3 bond, meaning this carbon has had a hybrid orbital, which is sp3. It hybridized in order to form the bond, and this carbon did the same. And so this bond would be sp3 to sp3. All these other bonds, for example, this one over here, would be an sp3 to an S, because hydrogen only has 1 electron in its outer shell, and that electron is in the only possibility for its orbital, which is an S. So therefore it's an sp3 to S bond. These bonds that involve S orbitals are called, the Greek letter for S, a sigma bond. So these are all sigma bonds because they involve the S orbital. Now, this is ethane. Let's look at ethene, also called ethylene, because it ends in -ene, you know it's an alkene. All alkenes have double bonds. So here we have carbon, double bonded to carbon, hydrogen, hydrogen. Note, each carbon is only bonded to 3 other atoms. Because it's 3 other atoms as opposed to 4 in ethane, 3 hybrid bonds, so it's an sp2 hybrid. So these are sp2 to S bonds. So these are still called sigma bonds because they involve the S orbital. Here, we're going to have one of the bonds being sp2 to sp2. So that would be a sigma bond. But there's another bond, and that bond would be from the extra electron that wasn't used in the hybrid bond. Because it's called an sp2, that means, as we've just seen, it has 1 s electron and 2 p electrons. But when we looked at the carbon molecule preparing to bond, we saw that the carbon molecule would have in its outer shell 3 electrons in the p orbital. So there's only 2 in the hybrid bond. That means there's an extra p electron in each of the carbon atoms. So those p electrons are bonding to each other. And this p to p bond is called a pi bond. So that's a pi bond. The sigma bond is stronger than the pi bond. That's what I was referring to earlier when we talked about multiple bonds. The first bond, being the sigma bond, is stronger than the pi bond. But having 2 bonds certainly is stronger than just having 1. So we've completed our review of bonds. Now we're going to move on to gases. The fundamental concepts behind gases includes pressure, volume, and temperature. In terms of pressure, it is very important to remember that the units of pressure for the SI system is a Newton per meter squared. A Newton per meter squared is also called a Pascal. The other numbers that you must memorize is that 1 atmosphere is equal to 101.3 kilopascals. Kilopascals, in other words, that's 1,000 pascals. So that's 101 0.3 thousand pascals, and that is equal to 760 torr, which is equal to 760 millimeters of mercury. In terms of temperature, the key units for temperature, of course, are degrees Celsius. So if we have x degrees Celsius, that is equal to x plus 273 Kelvin. Because degrees Kelvin is the units that will be most often used when we are doing our calculations. So the conversion factor between degrees Celsius and Kelvin is 273. The next important concept in gases is that of STP. STP stands for standard temperature and pressure. Standard temperature and pressure is a temperature of 0 degrees Celsius, which means 273 degrees Kelvin, and a pressure of 1 atmosphere. Common mistake that students make is to use the standard temperature at 25 degrees Celsius. The reason some people make that mistake is because the standard temperature for liquids is 25 degrees Celsius, but the standard temperature for gases is 0 degrees Celsius, which is equivalent to 273 degrees Kelvin. The other important concept when discussing gases is that of partial pressure. The partial pressure of a gas in a mixture is the pressure that the gas would exert if it were alone. In fact, Dalton's law states that the sum of partial pressures in a mixture is equal to the total pressure. This is a very important concept, and it is commonly tested on the exam. For example, let's say that we have a container, and in the container we have two gases, oxygen and nitrogen. If in the container oxygen has a pressure, if it were in this container all by itself, it had a pressure of 2 atmospheres. And if in the same size container nitrogen had a pressure of 1 atmosphere, if we were to put both these gases in the same size container, the total pressure in the container would be the sum of the partial pressures of these gases. So the total pressure in the container would indeed be 3 atmospheres. Furthermore, as a result of Dalton's law, it is possible to state that the mole fraction of oxygen in this container is simply 2 over the total pressure, which is 3. So the mole fraction of oxygen in this container would be 2/3, and the mole fraction of nitrogen in this container would be 1/3. And this is a result of the fact that each gas acts independently in the container. So the pressure of the oxygen is the same pressure that it would have if it were alone. Adding nitrogen to the container does not alter the pressure caused by oxygen. But adding nitrogen into the container, if nitrogen adds pressure, therefore the total pressure will change. And you can calculate the mole fraction simply by taking the partial pressure of the gas divided by the total pressure in the container. Now, another commonly tested concept, that of Avogadro's law. Avogadro's law, or principle, states that for a given temperature and pressure, equal volumes of a gas contain equal number of molecules. And in fact, at STP, standard temperature and pressure, temperature of 0 degrees Celsius or 273 Kelvin, pressure of 1 atmosphere, we have Avogadro's number of particles. Avogadro's number of particles is 6.02 times 10 to the 23rd. And that is 6.02 times 10 to the 23rd is the number of particles per mole, number of atoms or molecules per mole. That's Avogadro's number, and the volume associated with this is 22.4 liters. Certainly, these are numbers to memorize. So, what is the significance of Avogadro's law? It is very important. What it is saying is that if we have, for example, two different rooms filled with different gases, the gases are at standard temperature and pressure. Now, these gases can be very different. One gas can be some normal gas like nitrogen, and the other gas could be something very complicated, some organic chemistry type of gas that's in that room. But both gases are at standard temperature and pressure. Well, Avogadro's principle is stating that if you take a container which is 22.4 liters in size and you walk into room A, you open up the container and you let the gas diffuse inside, and then you close the container. Then you can walk into the hallway and someone can go up to you and say, how many particles do you have in that container? Right away you can say 6.02 times 10 to the 23rd. You can go into another room with a completely different gas, open up a container which is 22.4 liters, allow the gas to diffuse in the container, walk into a hallway. Once again, how many particles do you have in that container? 6.02 times 10 to the 23rd. Just that straightforward. And if someone were to ask you, how many moles do you have in that container? You have 1 mole. Even if you don't understand the complexity of the gas, what the molecules are shaped like, you still know exactly how many particles there are in there based on Avogadro's principle. Meaning that you know if the temperature and pressure are standard and you have a container of 22.4 liters, then you know you have a mole, and you know you have Avogadro's number of particles in every mole. So to make this as practical as possible, whenever you see the number 22.4 on the MCAT exam, or any factor of that, for example, if you see 11.2, if you see 44.8, right away you should zero in on that. Those are volumes that should tell you something. 44.8 tells you we're dealing with 2 moles of a substance if it is at STP. And 11.2 means it's half a mole. And those are numbers that they will throw at you, and you have to immediately be able to recognize them based on Avogadro's principle. And certainly any factor of 6.02 times 10 to the 23rd is something that you should immediately recognize based on Avogadro's principle. Now we will look at the equation of state. Thus we have the equation of state. PV equals nRT. P, the pressure, V, the volume, N, the number of moles, R, the gas constant, and T, the temperature in degrees Kelvin. In terms of R, I usually memorize the R in terms of liters atmosphere per degree, and the unit that I remember is 0.08. That's the R that I remember. But you can remember R in terms of any of the units that you wish to, because depending on what units you use for pressure and volume, you will have different number for the gas constant R. But for me, I tend to try to put everything in terms of liters and atmospheres, and therefore 0.08 is the R that I tend to use. But you can use any one you want as long as you're consistent in any problem solving to make sure that all the other variables are in the same units as the gas constant that you're using. Now let's manipulate the equation a little bit. If we bring temperature over to the other side, we get PV over T is equal to nR. Now R is the gas constant. if you are not altering the number of moles, meaning you have a gas at a particular temperature and pressure and volume, and then you alter that in some way, but you don't change the number of moles, you're not adding gas to it or removing gas from it, well then you would get that PV over T is a constant. And what that means is that P1 V1 over T1 is equal to P2 V2 over T2. That's if you're changing the pressure before and after, the volume before and after, and the temperature before and after. So you have PV over T is equal to a constant. Now let's say that you were not changing the temperature. The temperature was remaining constant, but you were changing the pressure and volume. Well, then you would just take off the variable temperature, then you would get PV is a constant. That means that P1 V1 is equal to P2 V2. And once again, if you weren't changing the volume, then the volume would be constant. And therefore, you would have P1 over T1 is equal to P2 over T2. And finally, if the pressure was constant, then you would have V1 over T1 is constant. So there, V1 over T1 is equal to V2 over T2. So these are different ways that the equation of state can be manipulated or changed to be altered for specific situations. Of course, they're given specific names, but that's not as important as in terms of how you can use the equation to solve problems. The other manipulation, which is often used on the MCAT exam, is the following. Number of moles in terms of mass and molecular weight is equal to mass over molecular weight. So we have PV is equal to mass over molecular weight RT. So this is equivalent to PV equals nRT, because of course mass is in grams, molecular weight is in grams per mole. So if you cancel the grams, then you get moles on top, and that's the same thing as being the number of moles. So that's just dimensional analysis, looking after the units. So if we were to write the equation this way, if we were to divide both sides by volume, this is what we would get. Pressure is equal to mass over volume, RT, and we bring the molecular weight over to the side. Molecular weight. Why is this manipulation so important? Because when we talk about gases, sometimes instead of simply providing the number of moles, they may provide you with the density. And mass over volume is density. So this here becomes R rho, or D, depending on how you symbolize density, but usually density is symbolized by the Greek letter rho. And so we have pressure is equal to density times RT over molecular weight. So this is how they can ask you a question and you know the equation PV equals nRT, but you didn't remember how does density fit in, but then you make this simple change or alteration in the equation in order to see how density can fit into the equation. Graham's law. Graham's law deals with the rates of diffusion and effusion. Diffusion is defined as the spontaneous spreading of a gas through another. Of course, in reality, diffusion is the spontaneous spreading of anything through another. After all, liquids diffuse, and even solids diffuse. Rocks diffuse into rocks over millions and millions of years. And in fact, if you sat down long enough, your butt would diffuse into your chair. Of course, that takes a lot more time than this video will last. Nonetheless, effusion is the streaming of gas through a fine hole. The rate of either diffusion or effusion is given by 1 over the square root of the molecular mass. So this is more of a proportionality. So the rate is proportional to 1 over the square root of the molecular mass. Essentially, what this is saying is, if you have a heavy particle a particle that has a great molecular mass, many, many grams per mole, that particle will diffuse slowly because it is the inverse of the molecular mass. Therefore, the rate will be less as you increase the molecular mass. The bigger the particle, the more the inertia, the slower it will diffuse or effuse. The smaller particles will have a greater rate of diffusion or effusion. Now we're going to look at liquids. Vapor pressure is one of the fundamental concepts to do with liquids. Let us consider the following. This is a petri dish, and in it there's just some liquid. For example, let's say there's water in here. And then this is a bell jar. So it creates an enclosed space. Well, if we were to place the petri dish inside of this enclosed space, this bell jar, what would happen is that if we were to look just at the surface of the water, we would see that there are some molecules at the surface of the water that have enough energy necessary to enter the vapor phase. There's also going to be some molecules near the surface of the water that are going to condense and go from the vapor phase to the liquid phase. Well, because this is an enclosed space, there's going to be molecules going into the vapor phase, other molecules going into the liquid phase, and after a while, there's going to be a dynamic equilibrium, meaning the amount of vapor and the amount of liquid will be constant. So that's an equilibrium, but it's a dynamic equilibrium, meaning there's still a lot of motion going on because molecules are still going into the vapor phase and coming back into the liquid phase and going back and forth. So there is a motion that is occurring, but an equilibrium has been obtained. Now, let us imagine that we can go right into the surface of the water and see exactly what's going on. What we will see is that there are little molecules continually entering the vapor phase, coming back into the liquid phase, entering the vapor phase, others coming into the liquid phase, and so on. So this is continually occurring on the surface. Well, the fact that there are these molecules that are continually entering vapor phase and coming back into the liquid phase and going up and down and so on, it is applying a pressure on the surface of the liquid. The pressure that is being applied, remember, pressure being force per unit area, and this pressure that is being applied on the surface of the liquid, that is what we call the vapor pressure. Now, let us look at some of the things that can affect vapor pressure. For example, let's look at two substances. CCl4. So that's called carbon tetra for 4 chloride. Carbon tetrachloride and water. Consider which of these two would have a higher vapor pressure. You may want to pause and consider your response. Well, carbon tetrachloride, which would be, of course, carbon has 4 bonds, therefore it's in the middle of a tetrahedron, so the molecule would look something like this. And of course, these are all polar bonds, like we've discussed before, but this is a non-polar molecule, so it has a 0 dipole moment. It's a non-polar molecule. This obviously is a polar molecule with a non-zero dipole moment, as we've seen before. And we know that this molecule engages in hydrogen bonds. So, if we had these two substances at the same temperature, which would have the higher vapor pressure? Clearly it would be carbon tetrachloride, because more molecules of carbon tetrachloride would enter the vapor phase, because there's not something holding it in the liquid phase. So they'll have more molecules in the vapor phase, and therefore that's capable of applying greater pressure on the surface of the liquid. as opposed to water, which has hydrogen bonding. Therefore, the liquid phase is being held together by these hydrogen bonds. There's much fewer water molecules entering the vapor phase. Therefore, because there's less vapor, there's less pressure that could be applied to the surface of the water. Therefore, intermolecular forces have a great effect on the vapor pressure. Now we just looked at how some particles have enough energy to enter the vapor phase. Well, the Maxwell distribution plot will allow us to calculate more precisely how many particles have enough energy to enter the vapor phase, or how many particles have enough energy to do whatever we arbitrarily decide we want to examine. The Maxwell distribution plot looks at a plot of the fraction of particles on the y-axis against the energy on the x-axis. When we look at particles and their distribution of energies at a given temperature T1, it has a bell curve distribution. The bell curve begins at the 0 point, and it has a certain distribution based on the amount of energy and the type of particles that are experiencing that particular energy. The important points about the Maxwell distribution plot include the following. First of all, if we have a temperature T1 and we have the same particles, and then we provide a higher temperature, so we're going to give it temperature T2, obviously that's going to give a distribution of energy which is higher because we're increasing the temperature, so we're increasing the energy of the particles. Well, the key point about the Maxwell distribution plot is that the curve does not simply shift over when you increase the temperature. Rather, the curve always begins at 0, and then the curve, as you get higher and higher energies, the curve will simply not rise as high. It will remain flatter, but it will go further. So this temperature here will be T2, where T2 is a greater temperature than T1. So here we have, the reason why this is so important is because on the MCAT exam they can easily ask you about what change would there be in terms of the distribution of particles, and then they'll draw a bell curve starting at 0, and they'll ask you what happens at a higher temperature. And then one of the possible answers will be that the bell curve shifts to the right. And of course, many students will put this as being the correct answer because there seems to be some logic associated with that. But it is not logical for the following reason. That is that no matter how much you increase the temperature, there's always going to be some particles that are going to have a low energy. That's a normal distribution. Furthermore, if you imagine these particles having more energy and bouncing around and hitting each other, there's going to be some collisions of these particles that will occur in such a way that a particle will have a low energy even if it's just for an instant, because it was hit by many particles at a particular angle at a particular place in the container. And so the curve will continue to spread out, go further, but it would flatten out. And so more particles experience a higher energy, no doubt about that, but there will always be some particles, though a small fraction, that will experience lower energies. If you had to calculate precisely how many particles have a particular energy or higher, then you look at the area under the curve. So say that you wanted to look at the energy right here, and you wanted to know how many particles have this energy or higher. And say that happened to be the energy required to make a particle enter the vapor phase, or to make the particle boil, or something of that nature. Then what you would do is you would look at this point here, and then you would examine the area under the curve. And it's not as if for the MCAT exam, you need to do integrals or any complicated mathematics. It's very basic math. But it's just the concept that the area under the curve will provide you with the number of particles with this energy or higher.